yellow sheet out next to your notebook so that if you have it filled out, you can kind of verify, like, yes, I found that pattern already. And you can fill in your notes and maybe even fill in some of the blanks on the yellow sheet if you have them. I would still like for you to have the yellow sheet completed. So if you're doing that today in class while we go over the notes, that's fine. If you're doing it on your own tonight through the investigation or by looking at your notebook, any of those things are fine, but you should have that yellow sheet completed before your quiz on Friday. It's a good study tool. So we're going to focus on section 8 today and tomorrow. We are going to be doing graphs of polar equations both days. Today we're going to focus on the circles and the roses, or circles and rose curves. Tomorrow will be Limousin. Okay, and then quiz on Wednesday. So if you're gone tomorrow, check online, get the notes, watch the video. I'll post the worksheet tomorrow. But be ready for a quiz on Wednesday if you can. Okay, we're going to start with circles. These are the 3 equations for a circle. Okay, I would jot them down in my notebook. Each of the 3 equations has some of its own special characteristics, but in a lot of ways they have some big similarities too. So r equals a times cosine theta, and r equals a times sine theta. The r equals a is probably the most similar to like what we're used to in terms of like geometry circles and our rectangular equation for a circle. So r equals a, we also kind of saw that when we were doing section 10.7 last week. It's a circle that has a center at the pole on the polar grid, and r in this case would literally mean the radius, and so we know the radius is a. So if I'm drawing a picture of a circle that looks like r equals a, it would be centered at the pole, and then a would be the value of my radius. So, like if I gave you r equals 3 on a polar grid, you would just go out to the third circle, trace that third circle, there's a circle with radius 3. Easy. R equals a cosine theta and r equals a sine theta. Those are the graphs you guys focused on in the graphing investigation. Can anybody share, like, what's the big difference between those two? Like, how do they differ? Anybody notice what's different from cosine and sine?
Well, different from r equals a, that's instead of the center being, the pole is the middle point, right?
The pole is like the origin, the intersection of the axes.
Instead of the pole being in the center, the pole is on the end.
Yeah, so the pole is actually on the circle as opposed to the center of the circle. Okay, so that would be different from r equals a. Anything else? Differences you notice between those two?
The sine kind of forms itself around the y-axis, and the cosine forms itself around the x-axis.
Okay, the big difference, and something that you'll want to pay attention to for all of our graphs, is like the orientation of the graph is determined by whether it's a sine or a cosine function. So Mason said the sine circle, r equals a times sine theta, is really kind of formed around the vertical axis, okay? And that would mean it's symmetric to the vertical axis, okay? Whereas r equals a times cosine theta is really formed on the horizontal axis, so we would say it's symmetric to the horizontal axis, or you could say the polar axis. So here are some things that I'm going to talk about that first statement on both of those in just a little bit, but these are some additional things that you could write down. So r equals a times cosine theta starts at the horizontal axis and is symmetric to the polar axis, whereas r equals a times sine theta starts at the pole and is symmetric to the vertical axis. And I'll draw an image of what that could look like. Did you notice anything about A when you were graphing those in the calculator? What did A now represent? It's more of the diameter as opposed to a radius. So you would have seen as you were plugging in different numbers for like A times cosine theta, as you change the value of A, you actually change the whole width of your circle or the diameter of your circle. So I would draw that into my picture as well, making note that now this whole piece is really the value of A. So if we kind of go back to Mason's thought as well, like the center of the circle is no longer at the pole, could you identify where the center of the circle is on these graphs? Yeah, it's at half of A, and that will either be the X or the Y coordinate, depending on the orientation of the circle. Okay, so that's an interesting side piece that we could figure just by thinking about our orientation. I'm going to talk really quickly about those two statements I have that say it starts on the horizontal axis and it starts on the pole, because that's going to affect us when we do our examples. I'm going to ask you for the number of zeros on a graph. And when we're talking about polar graphs, zeros are at the pole. So the number of times that you cross through the pole. That's different than formally what we've always talked about as zeros is anytime we cross the x-axis. Now we're only focused as a zero as the time we cross the pole. So if my r equals a times cosine theta starts on the horizontal axis, that means it starts away from the pole. If you were to graph this in your graphing calculator, type in 5 cosine theta in its polar mode, you should see that when you actually hit the graph button, it would start out on the horizontal axis. It would not start from the pole. Okay, so it's going to start graphing over there. So to make the whole circle, think about how many times you have to cross the pole. That's how many zeros you have. So let's say I go counterclockwise here. How many times do I cross the pole? 1 time. So I have 1 0. So when it's r equals a times cosine theta, you'll have 1 0. Okay. If it's a sine graph, how many zeros would you have, considering that it starts at the pole? So it starts at the pole, that counts as a 0. To draw the first full circle, how many times would you cross the pole? Once to start it, and twice to end it. So if it's a sine graph, it would actually have 2 zeros. Okay. Remember, 0 means number of times it crosses the pole. Okay. So what we would consider the origin or the intersection of the two axes. Okay, let's look at an example. The example that you see is set up very similar to your assignments for today and tomorrow. So if you look at your goal sheet, you have worksheets for both days, today and tomorrow, and they're set up with the same information. You get a polar grid, so you don't have to draw that when you're doing your homework assignment. And then off to the side, it's going to ask you these same things. Give me the shape. Give me the max R value. Give me the number of zeros. Tell me what those zeros are. And then make a table of some significant points for your graph. And we're going to walk through all of that in this example and a couple others for rows curves. Okay. So make sure that you feel comfortable. Ask any questions that you have about how I'm filling any of that out, because those things will be graded on a quiz on Wednesday. We're looking at the equation r equals -5 sine theta up there in the top left corner. And, comparing it to the last slide, r equals a times cosine theta, r equals a times sine theta. I mean, this pretty clearly fits with a circle. So what is the shape of this graph? A circle. We'll show, when we get to the rose curve example, how can we tell the difference between a circle and a rose curve? Okay, we'll talk about that. Max R value is when you're putting in different numbers for theta in this function, what's the highest value you'll ever get out for R? And we could think about what that would be think about what kind of numbers you're even allowed to get out for a sine function. So either think about sine on the unit circle, or think about the graph of the sine function. What's the max value of the sine?
1.
1. The highest sine value that you'll ever have, opposite over hypotenuse, is equal to 1, right? Okay. So if sine is equal to 1, then r would be equal to -5. Okay, so -5. What's the lowest sine value you can ever have? -1. Okay. If sine of theta is equal to -1, then -5 times -1 would be +5. So what's the max r value for you? 5. +5. You could write off to the side here, your max r values can be whatever the absolute value is. To me, in polar graphs, 5 and -5 are really the same thing. The -5 just tells me to go in the opposite direction of the angle, like for a polar coordinate. So when we're thinking about that, they're both the furthest they could be from the pole, but you can just write the max r value as the absolute value of A each time. Number of zeros, since this is r equals A times sine theta, how many zeros should it have? 2, because it starts at the pole and it must end at the pole, so it's going to cross the pole twice. So we're going to say the number of zeros is equal to 2. And now we've got to find the zeros. Okay. So remember that to find the zeros, that means we want to know when we're at the pole. To be at the pole, your r value must be 0. So we're going to plug 0 in for r. 0 equals -5 sine theta. And solve for theta. First thing I would do is divide by -5. You're always going to divide by your a value, 0 divided by a, so it's always going to be 0. So I could even shorten my work that I would do in the future. If it's a sine circle, it's just going to be when is sine theta equal to 0. If it's a cosine circle, it's going to be when is cosine theta equal to 0. That's really what I need. Okay. And now we need to get the number of thetas that matches the number of zeros that I set up here. So I need 2 theta values that give me 0 for sine of theta. Okay. So where would my zeros be? The sine of 1 is 0.
Yeah.
1 radian, 1 degree. Think about the unit circle. Where is sine equal to 0? On the where? On the horizontal axis. What angles are those? 0? Yes, 2 pi. If you went back, that's the same one. What's the other one though? 180 pi.
I was thinking right.
But I don't think 1 or a -1 works. Because you're listing an angle, right? Okay, so beware of that. So we say 0 and pi. Okay, and then here's how I'm going to do my significant points. And I'll do this for all my graphs. My first 2 zeros, which happen to be 0 and pi, I'm going to put in for theta. 0, I'm going to leave a little space, pi. And because they were labeled as zeros, I know what r is for both of them. It is 0. Okay. Plotting those points are not very helpful. Where are zeros located? At the pole. Okay. So I need a point that's not going to be right at the pole of my graph. So I always choose the angle that's directly in between my 2 zeros. So what's right in the middle of 0 and pi? It's pi over 2. Now you just have to figure out, if you put pi over 2 into your function, what is the r value that you would get out? So I'm thinking r equals -5 times the sine of pi over 2. What is the sine of pi over 2? 1. R equals negative 5 times 1, so R equals negative 5. So I now know the R value right there is negative 5. And then that's a point that can get me out to like the other side of my circle, away from the pole, okay? And I am plotting this point, negative 5, comma pi over 2, just like we did last week. Since R is negative 5, I'd go out to the fifth circle, which is my last circle. I would go to the angle pi over 2, which happens to be my 90-degree or positive vertical axis. But since R was negative, I need to graph in the opposite direction. So I'm going to be putting my point right here. And then I know those are like the two endpoints of the diameter of my circle. So now I just have to draw a round shape. Attempt a round shape. So you draw a circle from your pole. Okay, not terrible. Not great, but it'll work. And there's my circle. Now, stop and think for a moment. Does that go along with the things you thought would happen based on your investigation? So like, since it's a sine theta and it's a circle graph, it should be symmetric to the y-axis or the vertical axis. Is that true? Yeah, it's symmetric to the vertical axis. Since the R value is negative, instead of the circle being above the horizontal axis, it should be below the horizontal axis. Is that true based on your significant points? Yeah. Okay, that works. And since R was negative 5, that should be the distance across your circle, or your diameter, and if you count out from the pole to that point that you plotted opposite of it, you do get 5. Okay. Does anybody have any questions about what I did right there? So the weird thing is like, we graph the circle only on 2 points. But if you pick the 2 zeros and then the point exactly in between them, this point exactly in between them is always either going to give you your max R value or the opposite of your max R value. So I'm getting 5 or negative 5 there. And so that's going to be like that point way on the opposite side. Okay, and then I just have to draw a circle. Okay. And that will be true for like our other shapes. It will give us that point that we need. Next up, we're going to do rose curves. It'll give us that point out on the petal, far away, and then we'll just know to draw a petal instead of a circle. Okay, if there are no more questions, we will talk about rose curves next. These are your two equations for rose curves. R equals A times cosine n theta, and R equals A times sine n theta. When you are having problems all mixed together, like on your homework and on your quiz on Wednesday, how will you tell if it's a circle or if it's a rose curve?
There's a number before the theta.
If there's an n or a number before theta, right? So if it's just cosine theta or just sine theta, it's a circle. Good. Okay. If there's something that's being multiplied in front of that theta, 2 theta, 3 theta, 4 theta, 5 theta, then it's a rose curve. Okay, so that's how you'll be able to tell the difference between the two. Tell me what you know about rose curves. They're pretty. Good, yes.
They're symmetrical.
What do you mean they're symmetrical?
Like, if it's a sine one, it's like symmetrical on an axis.
Which one?
Uh,
What do you think?
the vertical one.
Vertical axis, right. So the sine rose curve is also symmetric to the vertical axis. The cosine rose curve is symmetric to the horizontal axis. So that's carrying over from circles to rose curves, and tomorrow for Limassol, that's going to be true as well. Okay, excellent. What else do you know about the rose curve just by looking at those equations? No, it's symmetry, sine or cosine. Did any of those other things tell you anything?
Many petals or something.
How many petals there are? Which value is responsible for the number of petals? N. N is doubled if it's even. So if N is an even number, you have 2 N petals, 2 times N. And if N is odd, you have end petals. So there's like a little rule that you'll have to remember. We're gonna write that down here in just a moment. Okay, if it's odd, it just has the number end petals. If it's even, it has 2 times that number petals. What else does the equation tell you? Besides the number of petals. What would A be responsible for?
The length.
The length of your petal, right? Just like it's responsible for like how far out your circle goes, the A value here is going to be like what's the length of the petal in the curve. Okay. Okay, so I have a couple things that I have up here. Cosine theta begins at the horizontal axis. Sine theta begins at the pole, and I'm going to, again, come back and talk about those. Those have to do with our zeros. Okay. But then we should add the things that we got from Mason, Jennifer, Lily, okay, those people. We should say cosine theta is symmetric to the horizontal axis, or polar axis. And sine theta is going to be symmetric to the vertical axis. For both of them, A is equal to the length of the petal. And N tells us how many petals there are. We should write the 2 rules for N. Something else that will be really helpful in graphing so that like, we don't have to make an extensive table of values. We can kind of do just like we did with the circles and do just about 3 of them and have enough information. We can use this idea that the graphs are symmetric, and since the graphs are symmetric, their petals must be evenly spaced. So we can also use what I'm going to call petal spacing to help us graph. It's like a shortcut to making a full table of values. To figure out your petal spacing, just think about the graph like a full rotation, a full 360 degrees, or a full 2 pi. Okay, so I usually think in radians, so I'm thinking about 2 pi. And you just need to divide 2 pi by the number of petals that there are. Okay, or 360 divided by the number of petals. Okay, so I'm going to say 2 pi divided by the number of petals. So if you have 4 petals, 2 pi divided by 4 will be pi over 2, or 90 degrees, and the petals should be evenly spaced 90 degrees apart. And this will help with your symmetry. Okay, so we'll use that. You'll see me use that in the example. The other thing that we want to talk about are the 2 pieces that I gave you underneath the 2 functions, which are where it begins. Because just like it happened for the circles, it's going to affect the number of zeros that you have, the number of times that you have to cross through the pole. Okay. So I'm going to do, right here, I'm going to do A equals cosine n theta, and I'm going to draw a picture. Okay. I'm going to do a 4 petal. I'm going to start on the horizontal axis, so I'm just going to start over here on the right. It could start on the left if the A value is negative. And I'm going to make 4 petal rose curve, and we're going to count how many times we cross the polar axis. Okay, so I'd start, and the direction would depend on the function and things like that. So I'm just going to go under here. So I'd cross once. Okay, there's me at the pole. I can't go back and make that pedal, otherwise I have to retrace my steps, so I have to do a different pedal now. So I have 1 cross, 2 cross, 3 cross, 4 cross, final shape. So I crossed the polar axis 4 times and I had 4 petals. So we could say that the number of times we crossed the polar axis was equal to the number of petals that we had. Okay. Now let's do a 4 petal rose curve that starts at the pole. Okay. So here I have 1, 2, 3, 4, 5. That one has an extra 0. Do you agree with that? Okay. And that one has an extra 0 because you started at the pole. To draw all of your petals, you have to go back to the pole. Okay. So what could we say about the number of zeros?
For cosine, you can say 0 is equal number of petals.
Okay, 0 equals number of petals. For sine,
0 is equal number of petals plus 1.
you need one more. Because you'll start at the pole and you have to end back at the pole. So that's going to be that double time. Okay. Do you have any questions about anything that we've written down in terms of information? Let's do an example of a rose curve. See how all these things come together to help us graph a rose curve without a graphing calculator. Okay, so we can do this without a graphing calculator. And the nice thing is on your homework, you'll be provided with a polar grid. So our equation is r equals 4 times sine theta. And again, pay attention to like when you're looking at the equation, how will you tell what shape it is? The n value is present here, so it's not just sine of 2 theta or sine of theta, it's sine of 2 theta, which means it's a rose curve today. Okay, so I'm going to say my shape is a rose curve. And this would be the other thing I'll tell you to do on your homework. Tell me how many petals right away. So call it a rose curve with 3 petals, a rose curve with 4 petals. Okay, whatever that may be. How many petals will we have? 4. 2 times n. N is equal to 2, which is even, so we double the number of petals that we have. Okay. So rose curve with 4 petals. What would be the max R value? 4. Okay, same as it was before. What should be the number of zeros? 5. That's the number of petals plus 1. Okay. And then find out what those zeros are. So just like we did for the circle, we'd set 0 equal to 4 sine 2 theta. But then of course that means that 0 is equal to sine of 2 theta. So you don't even really need to write the a, because you're always going to divide by it. It's going to disappear because you're doing 0 divided by that value. And then instead of just saying theta equals, we have to say 2 theta equals. Okay. So whatever your n theta is, you'll have to divide by n at the end. And you start by answering that question. What angles have sine values of 0 on the unit circle? The horizontal one. So the first angle would be 0.
360, because you would do 180 times 2. Or you divide that by 2. So
Well, what's the next angle? What's the next angle on the unit circle? Like you're thinking you start at 0. What's the next angle that has a sine value of 0? 180 or pi. And then that's only giving us 2 zeros. How many zeros do we want? 5 zeros. So what's the next one? 360 or 2 pi. And the next one? 3 pi. And the next one? 4 pi. So you have to keep going. You've got to list new zeros, okay, so that you get the number of zeros that there are. Okay, so we wanted 5 zeros, so I have to go 0, pi, 2 pi, 3 pi, 4 pi, until I get that number of zeros. What do I have to do with all of those now? Divide by 2. Okay. So I'm going to say divide by 2 right here. Divide by 2, divide by 2. And so when I list my zeros up here, I'm going to have 0, pi over 2, pi, 3 pi over 2, and 2 pi. So I'm going to have 5 zeros. Now, even though I'm listing out 5 zeros, I'm not going to put all those things into my significant values table. Like, I don't need that many. What I really need is a single petal. And once I have a single petal, I can use petal spacing to get my other ones. So I don't really need to do all the zeros and things in between all the zeros. Okay, so I'm going to pick my first 2 zeros, 0 pi over 2. I'm going to put them in my table. They're thetas, so I'm going to put them in. I'm going to leave space so I can do that one right in between, because these are both going to give me 0, which is not helpful. I need to know where that petal is going to go out to. So what's right in the middle of 0 and pi over 2? Pi over 4. So we're going to put pi over 4 here. And then you are plugging pi over 4 in for theta and figuring out what's that value of r. So we would do r equals 4 times sine of 2 times pi over 4. That's 4 times sine of pi over 2. And what's sine of pi over 2? 1. So that's 4 times 1, which is 4. So I now know that at pi over 4, my r value is 4. It's that max r value of positive 4. So I actually should plot a petal at 4, comma, pi over 4. And now give me my first petal for my graph. Starting at the pole, go out 4 on pi over 4, and then I would come back to the pole. So I can draw the petal. You know, in my mind, I'm thinking this is a rose curve, not a circle, so I'm not going to draw a circle. I'm draw a petal. So you're also thinking about the shape. For the other petals, I'll just use my petal spacing. So I'm going to take 2 pi divided by the number of petals, which is 4. So all my petals should be separated by 90 degrees, or pi over 4, or sorry, pi over 2. So my next petal should be at 3 pi over 4, 5 pi over 4, and 7 pi over 4. Going out to the 4. Now, you could get those same petals by extending this list of significant points. So I could do like 3 pi over 4 and then go out to pi and figure out what this value is. But you don't have to do that if you use petal spacing. Okay, how do you feel about that? Not bad? Real quick, I'm going to run through one that is odd and cosine, just so you can see it. Okay, so if you want to write it down in your notebook, you can. I'll move much quicker through the last example, just so we have one more done that you can look at. Okay, r equals 5 times cosine 3 theta, so I know it's a rose curve because of the 3 theta. And since n is odd, it has n petals, so it has 3 petals. The max r value is 5. When it's cosine, the number of zeros is equal to the number of petals. So we have 3 zeros. And what are the zeros? This time I'm going to do 0 equals 5 cosine 3 theta, or 0 equals cosine 3 theta. And so I'm going to say 3 theta equals, we already know sine, 0, pi, 2 pi, 3 pi, 4 pi. So when is cosine equal to 0? On the vertical axis, right? Pi over 2, 3 pi over 2, and since I need to get 3 zeros, I'm going to go, the next one is 5 pi over 2. And you could keep going if you needed more zeros. 7 pi over 2, 9 pi over 2, 11 pi over 2. Okay, it's going to be those odds. Divide all of them by 3. So be really careful here. When you divide a fraction by 3, you're multiplying by 1/3. So this will be pi over 6, 3 pi over 6, which I'm going to write as pi over 2, and 5 pi over 6. And so I got my zeros. And then I'm only going to pick my first two, put them into my table. Pi over 6 gives me 0. Pi over 2 gives me 0. You might have to do a little extra thinking, like figuring out what's in between pi over 6 and pi over 2. So if you treat pi over 2 like 3 pi over 6, what's in between pi over 6 and 3 pi over 6? 2 pi over 6, which is really just pi over 3. Okay. And then I would plug that in, so I'm thinking r equals 5 times cosine of 3 times pi over 3. That's really just 5 times the cosine of pi, which is -1. And so you'd get -5. Which that's going to help me when I'm graphing my first petal. Think about this polar coordinate. You'd go to pi over 3 angle, but because the r is negative, you'd plot opposite the angle. So instead of plotting in quadrant 1 where pi over 3 is, I'm going to plot in quadrant 3 where 4 pi over 3 is. So that would be my first petal. And then for the other petals, I'll use petal spacing. 2 pi divided by 3. So this is at -2 pi over 3, so there will be a petal over here on the horizontal axis, and there will be a petal in the second quadrant. You can tell, like, if you hold your paper away from you, if you have evenly spaced them or not. Okay? But you can also think about, like, where you are in the angles and what fractions you have, things like that, to get that right. Okay? Homework sign is super important. Tomorrow we're going to do the limicon, and there are several different types of limicon. Some that have loops, and some that have dimples, and some that are flat. Okay, so by doing more homework tonight and like really getting that significant point table, that's going to be super helpful for tomorrow, so that we can kind of run through those pretty quickly. I don't know if I have.
Sounds like croissant.